Thank you everyone for joining us. I'm Amber O'Brien. I'm the Ag Educator for Calumet County Extension, and I'll be your host today. And I would just like to give a thanks out to our sponsor, BioFirm, and I'm just going to share a video from them.
Based in Madison, Wisconsin, BioFirm Energy Systems offers fully integrated anaerobic digester, renewable gas upgrading, and solar energy systems based on proven technology that has been refined over the course of more than 30 years. From project conception through commissioning and continuing after adjusting the final bolts, we handle every aspect of the process. We also offer individual services, including consulting, preliminary design, feasibility studies, engineering, construction, commissioning, operations, maintenance, and spare parts. BioFirm is committed to providing successful renewable energy projects to our customers. We ensure our technologies seamlessly integrate into your operation and offer the industry's most thorough performance guarantee and warranty. We understand that as an operator of a dairy farm, manure management is one of your most important responsibilities. Anaerobic digesters and renewable natural gas upgrading are two systems that not only manage the waste, but also bring many benefits, environmental and financial, to your operation. These include reducing your carbon footprint and your reliance on traditional sources of heat and electricity, as well as introducing diverse revenue streams through the output of digestate and produced biogas. 1 ton of manure could generate $50 in renewable natural gas. If you would like to learn more, please send us an email at info@biofirmenergy.com or give us a call at 608-229-6518. We would love the opportunity to talk to you.
All right, so we have Dr. Horacio Aguirre-Villegas, and he is going to be speaking today. Dr. Horacio is a scientist at the Biological Systems Engineering Department at the University of Wisconsin-Madison, and his research lies at the intersection of climate change, energy, waste management, and food production. He has extensive experience evaluating renewable energy systems and integrating waste to energy technologies to increase environmental sustainability. Over the last 10 years, he has worked closely quantifying the environmental impacts of conventional and organic dairy systems, including greenhouse gas emissions, ammonia emissions, resource use, and nutrients fate. He's interested in evaluating different manure management practices and technologies that can be implemented in small and permitted facilities to reduce these impacts. He has received his doctorate's degree in biological systems engineering from the University of Wisconsin-Madison.
Thanks for that introduction. Thank you everyone for joining this track after lunch. Yeah, my name is Horacio and I am a scientist at the Biological Systems Engineering Department at the University of Wisconsin-Madison. And as Amber said, I've been working the last year environmental impacts of agricultural systems and more specifically dairies, and how different management strategies can help reduce greenhouse gas emissions and other environmental impacts. And today I'm going to focus on manure management and greenhouse gas emissions. If you were at this morning's talk, Michelle Watio presented enteric methane, so I'm going to focus on manure. So just to give you a broad picture, I'm going to start talking about greenhouse gas emissions in general, right? What about greenhouse gas emissions? We hear a lot about them. Then we're going to go more specifically into the dairy sector, and then into the manure management. And then I'm going to try to talk about each of the manure handling steps, more specifically the barn or manure collection, you know, what happens at storage, what happens at manure processing with greenhouse gas emissions, and after manure land application. So one of the first things that we think about when we hear, you know, the greenhouse gas emission words, there's like, think about probably climate change and global warming. So, and these two terms are something are sometimes being used interchangeably, but they are different. So global warming specifically addresses the rising temperature of the planet, and it's caused this by greenhouse gas emissions originated from human activities. And climate change a little bit broader, right? Climate change includes global warming, but it also has other effects, or intensive climatic effects, melting glaciers, high sea level rise, heavier storms, etc. And climate change can be caused by both human and natural activities. So greenhouse gases are gases that trap, right, heat in the atmosphere. That's why they received their names, because they make the Earth behave like as a greenhouse. And as we can see here in this bar here in blue, carbon dioxide, resulting mostly from the combustion of fossil fuels and the production of energy, is the main driver of emissions globally, and in this case we're looking at the numbers in the US. There's also methane, nitrous oxide, and fluorinated gases that have a lesser impact, but they are important as well because they have a bigger global warming effect we're gonna evaluate later. So of the total greenhouse gas emissions in the US, nearly 10% are coming from agriculture, and which involves the production of food, right? Crops and livestock production. And these emissions, as opposed to carbon-based emissions, are harder to quantify because they are based on biological processes. They can interact with other factors and variables like temperature, different environmental factors, but also different characteristics of in this case, manure. For example, manure characteristics, how much solids in the manure, how much nitrogen, etc. So there are different factors that make it challenging to correctly estimate and quantify the greenhouse gas emissions from agriculture. Some of the key characteristics of greenhouse gas emissions that I was telling you about, first, the abundance, so how much of a specific gas is available in the atmosphere, and this is very related to the amount of greenhouse gases that are emitted in each country and globally, right? So the most abundant greenhouse gas emissions resulting from human activities is carbon dioxide. Then there's the lifetime, so how long does the greenhouse stay in the atmosphere? And as you can see in this graph here, the lifetime of these different gases is different. Carbon dioxide can stay in the atmosphere from 300 to 1,000 years. Methane, even though the methane has a much higher global warming potential than carbon dioxide, 28 versus 1, it only stays for 12 to 15 years. Nitrous oxide has a higher global warming potential and also like 120 years that can stay in the atmosphere. And global warming potential, well, what is global warming potential is how strong is this gas in trapping heat in the atmosphere. So, and in order to standardize and make these greenhouse gases uniform, they are all compared to carbon dioxide. So how much heat can they trap compared to CO2? And methane and nitrous oxide are particularly important for livestock operations because they are the two ones that are emitted through, in this case, management during storage, during land application. So talking about methane, we saw that methane is more potent than CO2 in terms of its global warming potential. It's emitted by both natural and human activities, but most of the methane in the US from human activities. They represent more than 60% of methane emissions last year. And they come mostly from enteric fermentation, the rumination of livestock animals, the ruminant animals, and from manure management. There's also nitrous oxide. Nitrous oxide is actually 10 times more potent in warming the earth than methane, and 265 more potent than CO2. also produced by human activities. But here, agricultural soils are the dominant source of nitrous oxide. And this includes all the application of fertilizers and manure in the accounting. So you're going to see that the accounting of and the reporting of greenhouse gas emissions in inventories by different organizations usually include the application of the fertilizer in the crop production itself. What about carbon? So carbon can originate from fossil sources like fossil combustion, fossil fuels, but also from biotic sources, from biomass. But when carbon dioxide is emitted from biotic sources, it's considered that it's part of the carbon cycle, right? Because the plants were able to capture this carbon from the atmosphere that is stored temporarily in the plants, and then if you feed that to the dairy cow, then that gets converted into milk, into the meat of the cow itself, in manure, and along this process, there's some of that carbon that's going to be emitted back as CO2 into the atmosphere. When there's livestock, however, there's fermentation that interacts right with carbon, and some of that carbon is converted to CH4. So that's when the carbon cycle is not complete. And as you can see, like when we talk about fossil energies, well, you were taking fossil fuels from Earth, and then you're combusting them, and you're emitting CO2, but you're not capturing, you're not taking those emissions back into the Earth. So that's why the carbon cycle from biomass sources is very important. In terms of greenhouse gas emissions from dairy operations, we saw that agriculture is like around 10% of the contribution of greenhouse gas emissions globally in the US. Dairy approximately contributes 3% to these emissions. This number has been increasing in the last years. However, when you examine the milk production, right, that's the main function of dairy systems, to produce milk and give us this food that is rich in nutrients and vitamins. So when you analyze the actual production of milk, well, that has been increasing as well. So when you express your results of greenhouse gas emissions in terms of milk production, that plays a significant role. You're going to see that can decrease emissions because milk production has been increasing. Dairy is very important in terms of enteric methane, because you have a ruminant animal that carbon into methane. So dairy is responsible for around 26% of enteric methane, but 53% of methane in manure. That's why it's so important to think about strategies to reduce emissions related to manure management. In terms of nitrous oxide, around 4% of N2O from manure management. However, this does not include manure land application, as that is accounted in the inventories that are out there for crop production. So going deeper into the dairy farm, we can see this was an LCA life cycle assessment study conducted in the US in different regions, 2013. Then we can see a couple of things that I want to highlight, that the majority of emissions from milk production happen at the farm level. So around more than 70%, including the production of feeds, enteric methane, manure management, and the energy that is used in the farm. And manure management is the second source of emissions. And mostly in green here, methane from manure storage when dealing with liquid and slurry storage systems, and nitrous oxide from soils. So there are multiple different factors that create the optimal conditions for manure to generate greenhouse gas emissions, right? So there are different processing steps. bark manure that is collected at the barn. There's manure that is stored. Right? It can be processed. So there are different steps. So as more steps we have, there's more opportunity for emissions to happen. Also, there are the characteristics of manure. Manure has volatile solids. Manure already has gone out fermentation. Has methanogenic bacteria in it, so it can produce methane, for example, more easily. And the dairy cow can produce a lot of manure, right? More manure than milk, actually. As you can see some of the numbers here of an average milking cow produces 36 kilograms of milk per day, but it can produce 61 kilograms of manure per day. So there's a lot of manure, and as you all know, that has to be handled. So in terms of manure management, now we're going more into manure management itself. There are different sources of emissions. The manure itself, like I just said, so there's methane and nitrous oxide that can happen due to biological processes from the manure. There's the energy also that's needed to handle this manure, so transport and land apply. For example, if there's agitation in the manure storage, there's energy that is needed in the form of diesel or electricity, depending on the agitation, the type that is being done at the farm, and also indirectly from ammonia emissions. So ammonia is not directly a greenhouse gas, but ammonia can be transported long distances, and eventually can be through nitrification and denitrification to N2O. It can deposit into water streams or soil systems and then be transformed into N2O. So it can contribute to greenhouse gas emissions indirectly. And it's important to talk about ammonia emissions, like I said, because there has been warning about ammonia. Around 50 to up to like 70% of the nitrogen excreted in the cow can be lost as ammonia, and it has health as well as environmental implications. Not only because it indirectly contributes to global warming, but there are also other effects that are not very nice. And also, if you're using manure as a nitrogen source, right, you're losing money really in that volatilized ammonia. So in order to understand the different emissions that happen throughout the manure management life cycle, we need to understand what are the components. So we talk about manure collection. So there's manure right after it's excreted. There's like the collection process that takes place, or the barn, the manure that stays in the barn. So that can be processing. We're going to talk about that, and then storage in majority of farms, either solid or liquid, and then land application. And it's very important to think about all these stages and also the different characteristics of manure, because they are directly related to the amount of greenhouse gas emissions. So for example, this graph shows the results of a survey we conducted some years ago in Wisconsin dairy farms, and we see that small farms tend to manage solid manure, whereas as large farm size increases, then big handled by permitted facilities and large farms, and larger farms need farms that handle liquid manure need storage, and that is very important for methane emissions. Okay, so in this graph, like I just said, this graph shows the greenhouse gas emissions at each of the manure handling stage. So it gives us a general picture of what's happening. And this is a result of an LCA study that we modeled in, I know, Wisconsin dairy farm some years ago. You can see that during collection, and in this case, that sand was using bedding as sand as bedding. the greenhouse gas emissions were dominated by methane during storage, and this was a farm handling liquid manure. And then we can also see that during land application of manure and after land application, N2O emissions are the big players here. But when analyzing a farm, a smaller farm, and this was actually an organic dairy farm, around 100 cows, that didn't handle liquid manure, just solid manure, we can see that methane is not an important contributor to greenhouse gas emissions, but nitrous oxide is. So it is important to think about what type of manure handle, because the conditions that manure interacting with environmental factors, right, such as temperature, and if it's an aerobic or anaerobic environment, is going to promote one type of emission or the other. So, go quickly through each of these manure handling stages. Like I said before, the barn is not the major source of greenhouse gas emissions. It can be an important source of N2O in bedded packs, because the conditions that take place during bedded packs, it can be stored, manure can be stored along with bedding for like up to 6 months. Temperature increases, there's carbon there available for microbes to produce N2O emissions. And this graph here in the right actually shows the different processes, how, ammonia and nitrous oxide are produced. After manure is excreted, you have the nitrogen in manure, and if it's in the form of ammonia, that can be easily be lost or volatilized as ammonia if it's not incorporated into the soil. And this happens in the barn because there's less opportunity for the nitrogen, right, to bind into the soil. So ammonia emissions are very important for at the dairy barn level. Like I said before, ammonia indirectly contributes to greenhouse gas emissions. There are strategies to reduce ammonia emissions in the barn. Right, ammonia emissions is promoted by high temperature, moisture. If there's wind and if the manure is exposed, there's a big area, so there's more exposure of manure to wind. pH, the manure, if it has more ammonical nitrogen, also there's going to be, of course, more nitrogen that is being lost. So trying to kind of handle all these factors can mitigate emissions. For example, if you collect manure frequently from your barn, so there's less opportunity for emissions to happen. Avoiding porous floorings, so nitrogen stay there, and in moisture environments for ammonia to happen, or N2O emissions also. Then if you provide an organic bedding source, right, so that nitrogen or ammonium can bind into that bedding, can be also something that could reduce ammonia emissions, but we have to be careful there because it could also increase N2O emissions. There's another practice about talk about segregating manure feces from urine. I think this is not very common. I'm aware of just a couple of farms that are doing it, but it's in theory it should work. When we see the storage, when we think about storage of liquid manure, then right, we think about this picture shows a spontaneous combustion actually of methane in a manure slurry system. So why is it so important? Because it generates the perfect conditions actually for methane, right, to happen. It's high in moisture. The manure, it has volatile solids. If there is not an organic crust that forms on top, the manure storage is anaerobic. So the microbes love anaerobic conditions for methane production, and related also to temperature. So the higher the environment, the temperature, the higher the opportunity for methane to be emitted from liquid or slurry manure storages. N2O emissions from liquid manure storage are also depend on the aerobic versus anaerobic conditions. So if you think about a natural crust formation on top, that creates aerobic conditions on top of the storage. And you need those aerobic conditions for N2O emissions to happen. So when there's a crust, which happens for slurry manure with total solids more than 8% approximately, so those aerobic conditions and the mix of aerobic and anaerobic conditions that promote nitrification and denitrification then result in N2O emissions. If there is no crust formation, which happens, for example, when manure is being separated or after digestion, then there's no crust formation, so there's no N2O emissions under totally anaerobic conditions. As with ammonia emissions in the barn, there's also during storage there are also ammonia emissions that depend on the ammoniacal nitrogen concentration, the surface area of the storage, because there's more opportunity for that nitrogen to be emitted, and if there's wind, then there's more volatilization of nitrogen as ammonia, high temperatures, and then, like I said, wind is a key factor here. So whenever there is a cover or a manure crust formation, ammonia emissions are reduced. For solid manures, as stored on stacks generally, right? On stacks, on piles, methane emissions are not as important, but nitrous oxide emissions are, because there's a mix of aerobic and anaerobic conditions. Actually, these values here in this table present some of the IPCC. The IPCC is the intergovernmental, which is the key authority for climate change globally. And we can see that these are their emission factors of how much nitrous oxide is emitted per kilogram of nitrogen excreted. And you can see that the liquid slurry here, depending on that crust formation or not, on the management practices, N2O emissions can be 0 up to 0.005, which is the starting point for solid storage. So more N2O from a solid manure. And it can be as high as 0.07 in a bedded pack system. So in bedded packs, that's the main source of emissions from manure. Ammonia emissions also are important for solid storage. There's been some studies suggesting that they're kind of reduced versus liquid, because you have liquid manure, because you have a lower surface area, and there you have more resistance to loss throughout the bulk of manure. But there are also other studies that suggested the opposite. So more research is needed in terms of ammonia emissions compared to liquid, from solid storage compared to liquid storage. So some of the strategies that can reduce greenhouse gas emissions from storage, manure processing, there's many manure processing technologies available out there. We saw a couple this morning, and some of these technologies, probably the majority, have greenhouse gas emission reduction as the target, right, as the objective, but they also have an effect on greenhouse gas emissions. And probably the most important one has been, and probably the one that you've been hearing more about, is anaerobic digestion. Let's talk about that technology. But first, this graph just shows, based on that study that I talked to you, presented before, about that survey that we conducted in Wisconsin farms. We saw that the farms that actually adopt processing, that have some kind of processing of manure processing, mostly process manure through anaerobic digestion and solid liquid separation. There are some other farms that have some other processing technology in Wisconsin, but anaerobic digestion and solid liquid separation are the most popular ones, and they are adopted only in permitted facilities. So size, we already kind of knew, right, that economies of scale are important. Bigger farms can afford to have these technologies. There's composting as well. There's more popular in medium and some smaller farms. Okay, so what is anaerobic digestion? Is the breakdown of organic materials, in this case manure, in the absence of oxygen, right? So we are basically creating the optimal conditions and to accelerate the production of methane from manure and to get this biogas product that is reaching methane, like 6%, more or less from like 50 to 65% of methane, carbon dioxide, and other trace gases. So, so you have the manure system, and you collect manure, you put it into the digester. Most of the systems that have digesters in the US couple it with solid liquid separation in order to have more flexibility to manage this and take advantages of the benefits of the process. For example, high temperatures have been shown to reduce pathogens. So they have a solid liquid separation where you can, apply the solids as a soil amendment, probably transport it farther distances, and on the farm. And then you have the biogas where you can use it directly as a heat source, heat generation. You can clean it or upgrade. There's actually the last talk, I think it's about biogas upgrading. And probably the most popular use in the US has been cleaning and generating electricity and connecting that electricity into the grid. So what we're doing here, we saw that there are methane emissions from manure during storage, but here methane is actually a valuable product. So we're converting that methane into CO2 that has 28 times less, times less potent than methane in terms of global warming. And that CO2 is biogenic because it came from the biomass that the cow ate. So that's where the reductions come from when you have a digester in terms of greenhouse gas emissions. The other place for reduction, and this is something that is analyzed in LCA studies, is if that electricity or that biogas replaces grid electricity that is produced with a fossil fuel source, coal in the case of Wisconsin, right there, the grid in Wisconsin, 60% coal, 50 to 60% coal. Then if you replace that electricity, you have added benefits if those greenhouse gas emissions that are not emitted due to the production of the grid electricity. You're replacing that grid electricity with renewable biogas electricity. So those are other benefits that come into play when you have an anaerobic digester. They're interested in anaerobic digesters. There's a great resource from US EPA, ACSTAR. Now, currently there are 282 digesters in the US. Most of those digesters are in dairy farms. Well, I'm gonna go quickly through this, but manure is not the optimal feedstock for if you're just valuing the energy production during anaerobic digestion, but it's used because it's already available right in farm, and it also has some other benefits like odor reduction, pathogen reduction, etc. And that's why it's been used a lot in agricultural and livestock operations. So emissions from anaerobic digestion or after anaerobic digestion. After the digestion process, the digested has to be handled. So it can also be stored and then land applied or separated as we saw. And then a liquid fraction is going to be stored as well. So the reductions here in this graph in blue, we can see the negative numbers show a reduction in blue in greenhouse gas emissions. There are some other environmental impacts that we evaluated in this study. In yellow is ammonia. We evaluated solid liquid separation, anaerobic digestion, and a combination of anaerobic digestion and solid liquid separation. And greenhouse gas emissions are reduced, like I said, because of that methane that is not produced during storage after the digestion process. But there are also trade-offs, right? Because of the mineralization that happens during the digestion process, there is more molecular nitrogen now in manure. If you store without a cover, then there's ammonia emissions that are going to be increased, especially because also the total solids are reduced. There's probably less probability of an organic crust to form on top. So there are these trade-offs that we need to evaluate in order to try to minimize other environmental impacts that could happen downstream of anaerobic digestion. There's also covered lagoons, probably known like cap and flare systems as well. These are cheaper than anaerobic digestion. The most cap and flare systems just flare the methane. There's no energy production, but you could recover biogas as well and use it. But you are significantly reducing in a slurry or liquid manure system, storage system, you are significantly reducing your greenhouse gas emissions, because you're basically reducing all of the emissions of methane, except for any leaks that could be happening in your system. And there's probably the less complex of these technologies. Just use a manure cover right now with no flare, where you're going to also see reduction in emissions. There's different types of covers. There's the permeable covers, which are cheaper, but and probably have a shorter lifespan than impermeable covers, like synthetic liner or fiberglass, and that are more expensive, but are also have a longer lifespan and are able to control probably your nitrogen emissions a little bit better. Organic, for example, with the straw covers, then you have these aerobic conditions on top of the storage that may create conditions for N2 emissions to happen. We talk about the natural crust. We consider like a cover on top of the manure, but like I said before, there's these trade-offs that we need to analyze. Anaerobic conditions during storage would increase methane, but can decrease N2O, and on the contrary, aerobic conditions can decrease methane but can increase N2 emissions. So there's solid liquid separation, which can be done by mechanical technologies. The most popular is screw press and centrifuge, but it can also be done by gravity, in settling basins. The efficiencies of separation are different for these types of systems, and they vary in terms of cost and complexity. And they're mostly used to add flexibility for management of manure, but they also have an impact on greenhouse gas emissions. Well, this graph in a very simple way shows how the separation system works. This is a mechanical separator. We collect the manure, you mix it to make it more uniform, you pump it, and then you put it in your separator where you have your solids mostly stored before being transported and used as soil amendment on piles. And there's your liquids that can be more easily transported through pumps, for example, to reduce total solids. There's different efficiencies in terms of the separation technologies. Not all of the manure constituents separate equally. So that's one of the important things for greenhouse gas emissions. This study here that was published a couple of years ago actually classified the separators into low efficiency and high efficiency families. Low efficiency being like the screw press, the screens, and the high efficiency being a combination mostly of two technologies. Interestingly, they found that there are some centrifuges that achieve low separation efficiencies. And when I talk about separation efficiencies, how much of the solids go into the solid fraction of the manure, and solids and these analyzed constituents, volatile solids, total nitrogen, ammoniacal nitrogen, and phosphorus. Phosphorus is an important one because we have that problem right in Wisconsin. So we're trying to separate phosphorus, and we can see that high efficiency separators in this study achieve like 92% phosphorus removal. And this results here show there's variability. So in the previous farm, we saw that there's variability between separation efficiencies of the different manure constituents, but there's also variability within the same technology. In this study that we conducted a couple of years ago, we actually measured the components of digested manure, the digested and also pre-separated manure through a screw press. So there's 9 farms, 8 farms use screw press, 1 farm use centrifuge, and there's variability, as we can see, in terms of volatile solids and total solids and phosphorus. However, the farm with centrifuge achieved high phosphorus separation efficiency. So the phosphorus that stays with the solids, as was also presented in the other study that I showed you before. So solid liquid separation, the technology that can separate phosphorus. And what is important here for greenhouse gas emissions is that nitrogen, the majority of nitrogen, and specifically total ammoniacal nitrogen, really stays with the liquid. And so that's going to affect your N2O and ammonia emissions during manure storage and land application. So there, we saw that there are some reductions of greenhouse gas emissions from after solid liquid separation. And this happens because of the reduced volatile solids that go into the storage. And if you put those volatile solids into the separated solid fraction, right, that is stored in more aerobic conditions, so you're really reducing your methane emissions from the solid part as well. We can see that, you know, for a farm handling liquid manure, storage is the big player here for greenhouse gas emissions. So there's also composting. Composting has been around many years. It has many advantages. You have a product with less odor, you have less volume, you have a consistent product. There's a reduction in pathogens. It can deactivate weed seed, so it's great for soil amendment in gardens, for household application, etc. But it's an aerobic process, so despite that it can reduce methane emissions, it also creates the necessary conditions for N2 emissions to happen and ammonia emissions. So there are trade-offs in terms of emissions from composting. So the final manure handling stage, land application, depends also, the emissions also depend on the application method. Right, surface application of manure, which is more common in small farms, as we can see from the survey here that we conducted, result in more ammonia emissions. And there's also less frequency of application in smaller farms that from the farms that we surveyed. And as farm size increases, so there's no injection that takes place, and there's more injection through tankers and pump injection. So there's probably reduced, and there is actually reduced ammonia emissions, as you're going to see next. So it's important. The application method's also important. Okay, yeah, so this graph shows again the different components. Just want to highlight one time after several times how when you have a liquid manure storage system, how methane plays such an important role here, and that application emissions are dominated by N2O. If you have an anaerobic digestion system, your methane emissions during storage are really going to disappear. Are really going to, and most of your emissions are going to come from the land application of manure in the form of N2O. There's also some fossil emissions that are coming from the use of agricultural machinery for manure handling, and this happens mostly during manure land application more than the collection. There's more diesel that's being used, or more energy, like in the form of diesel, when manure is applied by tankers to apply manure than to collect, for example, manure in the barn. So the most important source for CO2 emissions to happen from is the land application. There are some strategies. If you have less total solids in your manure, you can use pumps to increase, the efficiency, your energy efficiency. Emissions, we saw how anaerobic digestion increase on the ammoniacal nitrogen, so it can increase ammonia emissions during storage. But if you have an injection application system, then this graph shows how your ammonia emissions after manure land application, after injection, can be reduced. And it's important because ammonia emissions happen really quickly if manure is not incorporated, and especially if there's more total solids in the manure, because it doesn't infiltrate as fast into the soil and then bind into the soil particles, so it's being lost quickly. So in general, both for ammonia and for N2O emissions, after manure land application, the management practices play a key role. So when you apply manure, it's very important you avoid extreme temperatures, that you avoid wet soil conditions and precipitation events, right? You match the application from when plants actually need it, so they can uptake that nitrogen. As we saw, your method of application, like injection, can reduce ammonia emissions, but it has been shown that it can also increase N2O emissions, as you are now creating some anaerobic conditions and opportunity for nitrification and denitrification to happen. The rate is important, so that's why it's so important to have nutrient plants to apply manure at agronomic rates in order to avoid nitrogen losses. Apply manure to growing crops or leguminous cover crops, right? Because they can uptake nitrogen more easily. Soil conditions, pH. It has been shown also that dry conditions tend to favor ammonia emissions, because of that mix of aerobic and anaerobic conditions can promote N2O emissions. Okay, this kind of again summarizes the emissions from the different stages of manure, but this study focuses on farm size. So a small farm usually doesn't handle liquid manure. So this is kind of like the reference scenario, and there's this low emitting scenario and this high emitting scenario based on management practices for a small farm, for a large farm, for a permitted facility. The smaller farm doesn't have slurry storage, so N2O emissions mostly happening here. In the larger farm, you have manure storage, so methane happening during manure storage. But when you have a bigger farm that has the economies of scale to put a processing system, in this case anaerobic digestion, we talk about how if you account for the benefits of replacing the fossil based electricity, the grid electricity, with your biogas based electricity, if you take those greenhouse gas benefits, then you can actually, your farm can become like a sink, right? Like you can sink of emissions because you're going to be avoiding more emissions than the ones that you are actually producing. So there are these opportunities that can happen at each stage of each manure, of the entire manure handling life cycle. If you're interested in greenhouse gas emissions in dairy farms, this is part of the Dairy Cup project that we finished some years now, but the virtual farm state. So there's a lot of information of greenhouse gas emissions and other environmental impacts at each component at the farm. Is very interactive. You can go to the virtual farm. This was a joint effort with multiple universities. You can send me an email if you're interested in about the information is presented here. We model 2 farms, 1,500 and 150 cow farm, and there's great resources here. There's also 13 fact sheets that we publish in terms of greenhouse gases and ammonia emissions from manure management and dairy systems in general, that you can access through the Learning Store at the University of Wisconsin. You can contact me as well if you want me to send you those publications. Actually, a lot of the information that I use for today's presentation use this information. Okay, so I think that's all that I have. Thank you so much for listening. I'm open to any questions.
Thank you very much, Dr. Horacio.
Thank you, Amber. Thanks, everyone.